Hello, my dear students. Welcome to the next subtopic of semiconductors. And in this subtopic, we are going to learn about the full wave rectifier, how the PN junction diode can be used in the full wave rectifier circuit. In the previous session, we understood the half wave rectifier. In the half wave rectifier, only one diode was used. That's why the efficiency of half wave rectifier was less because we can say it is half because the output we were getting for two cycles for positive and negative cycle, we were getting the output only in one cycle, that is the positive half cycle, while the output was zero in the negative half cycle. So the for one complete cycle we were getting only half cycle in the output side. So this decreases the efficiency of half wave rectifier. How it is overcome in the full wave rectifier we are going to learn now. So this is the full wave rectifier. The full wave rectifier circuit will consist of two diodes, and the two diodes will be operating alternately. For example, if suppose diode 1 is on, in that case diode 2 will be off, or if suppose diode 2 is on, then diode 1 will be off, such that the output will be present in both the cycles in positive as well as negative half cycles. But the circuit is drawn in such a way that the current will flow through a load resistance only in one direction, such that the reversal of current is not taking place. That means we have converted alternating current to direct current. So let us see what is the circuit diagram of this full wave rectifier. So this is the circuit diagram of full wave rectifier. I can say this is the 230 volts, 50 hertz AC supply, the constant supply for India. Okay, now this is the center tap transformer. Okay, this is the center trap transformer. The name of the transformer is also given to you, 2P3A. Okay, so this is the name of a transformer. This is the center tap transformer. From the center, there is a tap. Okay, it is connected to ground. The center it is connected to ground. So you can see that there are two diodes, D1 and D2, which is used in this case. Okay, so this D1 will work. It will be on in the positive half cycle. Positive half cycle it will be on. Okay, and in the positive half cycle D2 will be off, but D2 will be on in the negative half cycle. In the case of negative half cycle, this D2 it will be on. Okay, so alternatively, this diodes it will operate, and we can say in the positive as well as negative half cycle, the current will be flowing through the load resistance in the downward direction always. Okay, so we'll be learning how the current will flow shortly. Okay, so this is the input side. Input is 230 volts, 50 hertz AC supply. This is the transformer side. Okay, and this is the sender tap transformer. Two diodes are connected. The diode D1 it is connected to A, diode D2 it is connected to B, and this is the center tap transformer which is connected to ground. And after that, this is the load resistance connected like here. This is the P and this is the load resistance RL, which on the other side it is connected to ground. Okay, so I request you all to please draw the circuit diagram of this full wave rectifier so that you will be familiar with the circuit diagram. Okay, you practice the circuit diagram of half wave rectifier and full wave rectifier. You have to draw this in the examination. Okay, and this is the most favorable questions. Half wave and full wave rectifiers it can be asked in the examination. Okay, so these are the important topics: half wave rectifier and full wave rectifier. So we'll consider the positive half cycle. I will draw the circuit diagram once again. So this is the input side. Input side is 230 volts, 50 hertz AC supply. This is connected to transformer. So this is the center tap transformer. This side is connected to diode D1. This is diode D1. This is connected to diode D2. Okay, and they are joined like this. Okay, then there is a connection with the load resistance. This is the load resistance RL. The another side of the load resistance it is connected to ground. So this is connected to ground, suppose. And this is the center tap transformer. The center tap it is like this. It is moved like this. Okay, so this is the overall circuit diagram of full wave rectifier. In the textbook that ground it is shown here. So there is no issues. You can show ground anywhere. Okay, so anywhere on the same line. So this is the output VO and this is the input VI. So let us now see what is going to happen for positive half cycle. So I will be using different ink for positive half cycle. For example, I am using black ink. So this is what black color which shows the positive half cycle. So suppose this is the positive half cycle, the current flows from positive to negative always. So this is the current which is flowing from positive to negative. Okay, so this side is what positive, this side will be negative because this is the transformer and same will be induced, same polarity it will be induced. This is the center tap, it is connected to ground. So I can say this is P, this is what N, and again this is P, and N and P on the same point it is going to get cancelled and it will become zero. Okay. Now you see the polarity of the diode. This is the P type of semiconductor, this is the N type of semiconductor in the PN junction diode. Again, this is the P type and this is the N type of semiconductor in the PN junction diode. Now this positive is connected to positive and the negative it is connected to negative. I can say this diode D1 it is forward bias. Okay. While this D2 it is positive it is connected to negative terminal and negative is connected to positive terminal. I can say this is reverse biased. So in the case of diode D2, the positive is connected to negative terminal, negative is connected to positive terminal. I can say this is reverse bias. So in the case of forward bias, the diode D1 it will be on, while in the case of reverse bias, the diode D2 it will be off. So since if it is off, I can say you can replace this by an open circuit. So I will erase this part and it will be replaced by an open circuit such that no current will be flowing through this diode D2. Okay, so in what direction the current will flow? The current will flow in the direction which is I'm showing from positive to negative. It will start from positive. It will pass through this D1 because it is the short circuit. It is replaced by a short circuit because this diode D1 is on, and it will move in this direction, and again it will move through this RL and it will be shorted, like it will be passing to the ground. So in the case of RL, the current is flowing in the downward direction. The current is flowing in the downward direction like this. Okay. So if I draw a waveform, this is the input waveform. This is the positive half cycle. This is the negative half cycle. Again, this is the positive half cycle. This is the input side. What I'm getting in the output side is for the positive half cycle, I will be getting the same output as that of the input. So this is the same output I'm going to get as that of the input. Okay, so this is same as the half wave rectifier. In this case, D1 it is on. D1 it is on. So this case D1 it is on. Okay. Now let us consider the negative half cycle. Again, I will draw the diagram for the negative half cycle. So I hope you understood the positive half cycle. For positive half cycle, we are getting the same output as that of the input. Okay. The current through RL, you remember that it is moving in the downward direction, okay, towards the ground. Okay. Now we'll see the negative half cycle. Again, I will draw a circuit diagram for the negative half cycle. So starting from the input side it is same for both half wave as well as full wave rectifier. 230 volts, 50 hertz AC supply. Remember that AC should be written in small letters. Then there will be a transformer like this, and there are two diodes, the diode D1 and D2. This is diode D1, and here is diode D2. Okay, and these two are connected like this, and after that it is connected to a load resistance. So this is the load resistance RL, and this is the center tap transformer. Here is the output voltage VO, here is the input voltage VI, and this is connected to ground. Okay, now we'll say that the current flowing through the primary windings, it is nothing but the negative half cycle. Negative half cycle, that means the current is flowing in the opposite direction. For example, the current is moving in this direction. So the current always flows from positive to negative. This side is positive, this side is negative. So this is P and this is what N. Okay, this side is N. So this will be P. Okay. Now you look at the polarity of the diode. This is the P type of semiconductor. This is the N type of semiconductor. P type is connected to negative type. N type is connected to positive type. Now this D1, it is a reverse bias. In the case of reverse bias, the D1 diode, it will be off. Okay. While in the case of D2, this is the positive terminal of semiconductor. This is the negative terminal of semiconductor. Now this D2, it will be on. D2, it will be on, or we can say this is the forward bias. This is what a forward bias. Okay. This is what a forward bias condition. Okay. Now you see that P is connected to P and N is connected to N. P is connected to N and N is connected to P. So in this case, if it is reverse bias, it can be replaced by an open circuit. So this is replaced by an open circuit such that no current will flow from this. Since this D2 it is on, I can say it is replaced by a short circuit such that the current will be flowing through this diode D2 now. Okay, in the negative half cycle. Now what I'm going to Now what we are going to do is we will be drawing the current. So the current, it will flow from positive to negative. So this is the short circuit path where the current will flow. So current, it will flow from positive and it will move to the load resistance like this. And this will be the path, and the current will be flowing in the downward direction. Okay, so remember in which direction the current is flowing? In the downward direction. In the positive half cycle also, the current was flowing in the downward direction, and in the negative half cycle also, the current is flowing to the in the downward direction. So if I say this is the input side, so this is the input side, the waves are like this. This is the positive half cycle, this is negative half cycle, this is positive half cycle, this is negative half cycle like this. And this one is the output side. So in the output side, the current, it is flowing like this. This is the positive half cycle, the current is flowing. Okay, so we have already seen that in this case D1 is on. In the case of positive half cycle, the D1 is on. So this is what the D1 which is on. So D1 is on in the case of positive half cycle. But in the case of negative half cycle, D2 will be on, but the current will be flowing in the same direction. That means for the negative half cycle also, the current will be like this. The output current, it will be like this. Okay, so in this case D2 is on. So in this case D2 is on. Okay, right? So this is the case of full wave rectifier for both complete input waves, positive as well as negative half cycles. We are getting two output waves D1 and D2, right? So this is called as full wave rectifier, right? So I hope you understood the full wave rectifier. In case of any doubt, you can again watch the videos. Okay. So full wave rectifier output is like this. So if suppose this is the input waveform, this is the input waveform, okay, and this is the waveform for positive half cycle, and this is the waveform for negative half cycle, and this is the waveform, overall output waveform. So for positive half cycle, I can say D1 conducts. D1 conducts means D1 is on. So this is what D1 on, and in this is D1 off. In this case D1 on, in this case D1 off. While in the case of negative half cycle D2 conducts. D2 conducts means this is D2 which is off. Here D2 it is on. Here D2 it is off. Here D1 it is on. Okay. So you can see that there is an alternate, that if suppose when D1 it is on, then D2 is off. But if suppose D1 is off, then D2 is on. D1 is on, then D2 is off. That means it moves. That means it moves alternating. Okay, alternatively, that if suppose V1 is on, then V2 is off, but the current is always present. I can say output waveform is always present. Output waveform is always present. Okay, so here, if suppose input frequency is 50 hertz, input frequency is suppose 50 hertz, then output frequency is going to be 100 hertz. Output frequency is going to be 100 hertz. Why? Because we are interested in positive cycles. So this is the positive half cycle. We can say the output is present in the positive half cycle as well. Okay, so this is the negative half cycle. The output is present. Again, it is positive. So for one complete cycle, we are getting two positive cycles. So that means the frequency is getting double. Frequency is getting double. So remember that in the case of half wave rectifier, the frequency remains the same, but in the case of full wave rectifier, the frequency gets double. So the output frequency is double as that of the input frequency. Okay. What are the advantages of full wave rectifier now? The rectification take place in both the cycles. That means in the case of positive cycle as well as negative cycle. Next is the efficiency of the full wave rectifier is higher than that of the half wave rectifier. Why? Because in the case of half wave rectifier, for alternating pulse, we were missing the output. For negative half cycle, we were not getting the output. We were getting output only for the positive half cycle. But in the case of full wave rectifier, for positive as well as negative half cycles, we are getting the output. So that's why the efficiency of full wave rectifier is more. The ripple in the full wave rectifier is less than that of the half wave rectifier. Ripple, that means, uh, suppose I consider the diagram like this. So this is the waves in the case of half wave rectifier. So again this is zero, again this is zero, again this is zero. So I can say the ripple, that means the changes, okay, is what more. But in the case of full wave rectifier, the changes is less. Okay, the ripple changes is less. That's why I can say the ripple of full wave rectifier is less than that of the half wave rectifier. Okay, so this completes our topic of full wave rectifier. In the next topic that we are going to learn is the ripple factor. Thank you so much, all of you, for paying attention. Keep learning. Goodbye. Take care.